Now let's talk about curved space. And let's start with the space-time wrap.
Yo, Terminator X, step up on the stand and show these people what time it is, boy. Don't believe the hype. Don't believe the hype. Don't believe the hype. Don't believe the hype. Don't believe the hype.
Don't believe the hype, it's a sequel. As an equal, can I get this through to you? My 98 booming with a trunk of funk. All the jealous punks can't stop the dunk. Coming from the school of hard knocks, some perpetrate. They drink Clorox, attack the black because I know they lack exact the cold facts, and still they try to Xerox. The leader of the new school, uncool, never played the fool, just made the rules. Remember, there's a need to get alarm again.
Let's compare the worldviews of Einstein and Newton regarding space and time. These two very great scientists had completely different ways of thinking about the nature of gravity and space. Making this comparison throws into sharp relief just how dramatic and revolutionary general relativity was. To Newton, mass and energy are very different things. Space and time are very different things. Both are linear and infinite in extent. But to Einstein, mass and energy are interchangeable, and he links them formally with the equation E equals mc squared. And space and time are interchangeable, and one can be changed into the other in different situations in the real universe, and they are part of a four-dimensional construct called space-time. The Newtonian concept is that mass tells gravity how much force to exert, and the force tells the mass how to move. The Einsteinian concept is quite different. Mass energy tells space-time how to curve, while curved space-time tells mass energy how to move. Objects with lots of mass and energy will curve space and distort time nearby. Far away, the theory of Newton would apply. This only applies the Einsteinian theory in general relativity in situations where the gravity is very strong. As we'll see, close to a black hole is one example. But they also apply to large situations of curved space-time, like the universe itself. Mass and energy both cause space to be curved, and this curvature makes an observed bending in the path of light, as light follows the curvature of space. The deflection angle is small, for example, for a galaxy, causing the bending of light, or for the sun, causing the bending of a starlight, as in this diagram. This phenomenon is called gravitational lensing, or the gravitational deflecting of light. And it was predicted in the 1930s and finally observed in the 1970s, actually at my observatory here, the Multiple Mirror Telescope, when an image of a single quasar was seen as multiple images caused by this mirage effect of gravitational lensing. Here's Newton's view of space: rectilinear, rigid, not expanding or contracting. Just imagine a bug crawling over a fixed grid of graph paper, extending infinitely in all directions. These are two-dimensional analogies. We have to imagine this in the three dimensions of space that we inhabit. Einstein's view of space, somewhat different. It's curved and wavy. It also can be dynamic and expand or contract. Think of a bug crawling over a rumpled sheet of paper or rubber. In this view, space can have global curvature. Here's a two-dimensional space that's familiar and Euclidean. In space like this, whether in 2 or 3 dimensions, the angles of a triangle add up to 180 degrees. There's zero curvature, and parallel lines or beams of light through the space or along the space stay parallel forever. But we can also imagine curved space. This space is positively curved in 2 dimensions. An example will be the surface of a sphere. And we can see, trivially, that the angles on a triangle and some small region of the surface of a sphere always add up to more than 180 degrees. If you want an extreme example of that, imagine someone who's at the equator of the Earth, heads to the pole, takes a right angle, heads to the equator, takes another right angle, and ends up where they started. they've just described a triangle while moving in straight lines where the angles add up to 270 degrees. It's clearly non-Euclidean. So in spherical space, the angles of a triangle can add up to more than 180 degrees. Lines that are parallel do not stay parallel forever. Again, imagine two people traveling straight from the equator north. They will meet at the pole, and light beams in two-dimensional curved space would also converge, or three-dimensional space. So this is the positive curved situation. Also, we could have negatively curved two-dimensional space. The analogy for this in two dimensions is something like the surface of a saddle, that shape. Triangles drawn on the surface of a saddle add up to less than 180 degrees. Again, they deviate from Euclidean geometry. And if you draw parallel lines on a saddle shape, those parallel lines diverge, which is not what happens in flat space. So, Einstein described space that can have positive or negative curvature, or it could be flat, but flat is now just a special case of a whole universe of possibilities of curved space-time. If space that we live in, like the universe we live in, has positive curvature, it has a finite volume, but it has no boundary. Again, imagine a two-dimensional analogy of the surface of a sphere. You can travel endlessly along the surface of a sphere and never fall off an edge. There is no edge. This positively curved two-dimensional space clearly has a finite volume, or surface area, 4 pi r squared, and it has no boundary. And we can have three-dimensional versions of this, where the space is positively curved, has a finite volume, but also has no boundary. You don't fall off the edge of the universe. Both the zero and negative curvature cases are infinite volume and also have no boundary. The bard of gravity, Einstein, is timeless. That's the end of this topic.